Right, with that, we'll kick it off, Santi. I'll hand over to you and let's talk a little bit about scientific machine learning.
Excellent. Thanks for inviting me. I'm super excited to be here to talk about industrial grade scientific machine learning and challenges and opportunities. And the work that we've done and the results I'm going to present are collaboration with obviously RocketML and Iowa State University and New York University. So we have worked with a group of researchers from these universities. So my talk outline is going to be as follows. I'll quickly introduce what scientific machine learning is. You guys have been hearing about it for a while, so I'll try to make it a little more relevant for industry. And I'll talk about challenges and opportunities of scientific machine learning along 3 dimensions, right? So ambiguity, scalability, and deployability. So I'll kind of dig in a little more into these 3 specific topics and then summarize. So number 1, what is scientific machine learning? For the uninitiated, it's basically a field that is growing at the intersection of scientific computing, that is solving problems using laws of physics and scientific methods, and machine learning, right? So this is basically the intersection that is going. That is, how do you solve scientific machine learning problems using machine learning is basically the idea behind SciML. And looking at this from a point of view of data versus amount of information, the way to internalize SciML is on the left-hand side, you have scientific computing. That is, you have known physics, laws of physics, like you have your Navier-Stokes equations, Poisson equations, reaction diffusion equations to simulate different physics. And you solve those problems using traditional methods, right? Like finite elements, finite differences, and so on and so forth. And when you're solving these problems using traditional methods, you're not using any data. Right? The data here would most likely be geometry, etc., but not necessarily the data in the traditional machine learning sense. And on the other end of the spectrum is you use a lot of data and not so much physics. Right? So that is the traditional large-scale machine learning. Think of object detection, image classification on ImageNet data, and so on and so forth. What we have in between is basically this combination of physics. Basically, you're actually trying to put some constraints on your deep learning models using physics. At the same time, use some data to come up with the space of SciML. So there are significant implications working in this space, both from multi-scale simulations, trying to design new materials, inverse problems, et cetera, et cetera. Okay. So most of the talk will focus on this intersection of how do we introduce physics and also use data to build these ML models. So from an industry perspective, right? So I'll try to give the industry spin as much as possible. From an industry perspective, the value of scientific machine learning is extremely clear, right? So we talk to folks across several industries, and they get that if you pursue scientific machine learning and actually solve the problems, the time to solution is accelerated, right? So there is absolutely no doubt about the value. So for example, these are 2 of our publications where we have demonstrated that for a fluid flow problem, we can cut down the time to simulation from 400 seconds to 10 seconds in one case, and all the way from 6,000 seconds to 20 seconds in another case, right? So there's a heat transfer problem. So the value from SciML is extremely clear for industry, and you probably have seen a lot more papers and a lot more talks where this specific metric is probably demonstrated. But when you're talking about industrial grade scientific ML, right? So we are not just focusing on just solving a problem faster. We actually want to do something with it, right? So for example, you want to take that solver and design the heat exchanger in an aircraft, or design a drug for molecular simulations, or do molecular simulations for drug design, right? Or create these hip implants. So in all these cases, things like robustness of the models, right? And accuracy of these models and knowing when they break, there are a lot more operational and reliability issues that come into play. Right? So when we're talking about industrial grade, what we're talking about is this lab to bedside. So in healthcare, there is this lab to bedside concept where even though the drugs and new methods are designed in a lab in a university or in a pharma company, getting them all the way from there to the bedside, right, to real patients is a long ways to go. So in the case of industry, they're dealing with some challenges that are limiting the ability for scientific machine learning progress that is making in academia to go and be applied in industry. Okay. The first one is ambiguity. Okay, so let me dig in and explain what ambiguity means. Okay, so traditional solvers are fairly obvious for industry. Right? For example, let's say I take a Poisson problem, a simple steady-state heat equation problem, and the PDE is very clear. Right, I'm using this a second-order equation, steady state, so no time component. And typically, I want to pass in a control parameter, right? So in this case, a control parameter is input diffusivities or conductivities or several different applications, right? Porosity in case of fluid flow, and you pass that control parameter through a finite element solver, right? Finite element, finite difference. Pick your traditional solver. And out comes a state variable or the solution of the PDE. Okay. So the schema in the sense of traditional solvers is extremely clear. It's been established for the last 30 years. There are like hundreds of books on it. So this piece is clear. But when it comes to deep learning, there's a lot more happening. Right? So when I say there's a lot more happening, when you're talking about deep learning and ML, you're talking about, okay, there is training data. There is a concept of network architecture. Then we are talking about loss functions. Then we are talking about data representation, right? So, for example, you might have heard about pins, which have a pointwise kind of representation. You might have heard graph neural networks where the data is represented as graph. So when it actually comes to converting a traditional problem into a deep learning problem, there is this huge leap that the industry has to make. And because of so much work going on in this space, there is an inherent ambiguity and vagueness that is kind of building in the industry and has kind of good and bad implications, right? So good implication is like they know a lot of work is going on. The bad implications of this are, or the negative implications of this are, it's so much noise and so much ambiguity that they're not able to actually adopt these new innovations in for the day-to-day applications. Okay, so ambiguity leads to these problems. So let me dig into each of these separately in a second, but let me give one more example on pointwise versus full-field. Just sticking to this third piece here, network architectures, because you might have seen these pieces in the last few weeks in other talks. So just within the pointwise architectures piece of the ambiguity, we're talking about at least two types of architecture, right? One is pointwise, one is full-field. So within pointwise, the idea is the input to the neural network is a single point, and the output of the neural network is again a single point, right? So you're actually more going from point to point. And it has its own advantages, like it's a mesh-free solver. That means you do not need to have a mesh ahead of time. It's faster to train because you're dealing with smaller networks, and so on and so forth. But the cons are, it can only solve one instance of a PDE, right? For example, it's like a one-to-one. You have one PDE and you're solving one PDE at a time, right? And enforcing these boundary conditions, initial conditions for real practical problems kind of becomes non-trivial, because there can be a lot of homogeneity issues with respect to materials or geometry and so on and so forth. And enforcing the exact physics across all these different constraints is a non-trivial problem. Okay, and that leads to a lot of hyperparameters and a lot more fine-tuning. So that is pointwise. Then if we look at full-field, full-field is a set of architectures, a different kind of architectures, right? So for example, in this case, the input to the neural network is an entire field, like 2D, 3D, 4D in terms of time-dependent problems. And the output of this network is, again, full-field. Yeah. So the advantages of this are you can solve a parametric set of PDEs. So what that means by parametric set of PDEs is this model that you build is not just for one PDE, but it is actually, you can solve a set of PDEs using one network that you train. And this has practical applications in control inverse problems, and you can enforce boundary conditions and initial conditions exactly, right? So you can actually put some boundary conditions and everything on the input field itself, and basically that enforces your constraints exactly. But the cons of this are training this at scale is very expensive, right? So because you are talking about a lot of big data, because the data dimensions are not just point-wise, they're big. It takes a long time to train these networks. Okay. So the same thing with loss functions, right? So loss function can have different forms. So you can say, my loss function is based on FEM formulation, or my loss function is based on finite difference formulation. This comes from the traditional methods, right? So basically, we want to say my network is learning something about the physics, and I want to enforce this physics in my loss function. That's basically the idea of a lot of these data-free methods. And in that case, you can either define these loss function as an energy minimization or residual minimization. So there are different ways of actually just defining the loss itself. Okay, so hopefully this kind of gives you an idea of this. When you start digging into each and every piece of these four things, there's a lot more happening in academia that makes it extremely complex for industry to say, okay, what is this new method? What is happening here, and how do I use it? Makes it hard. So the opportunity, right? So because if you're looking, say, for some topics for your thesis or for your future research, the opportunities are as follows. One is there is still an open opportunity to come up with an ontology of for scientific machine learning, right? So starting with input data, right? So what is the input data that we want to use for training these networks? You can say, hey, my model is built for giving material properties the solution, or given boundary conditions the solution, or given a geometry a solution. So we need to come up with an ontology for just the input data. The second big thing is data representation, right? That is, how am I representing the data for my neural network? Am I representing my data, in this case, say material properties or any of these, as points, or am I representing it as voxels, or am I representing it as graphs? Okay, and there may be other representations that might come up in the future, but the going from data and its data representation itself is again an ambiguous thing that needs to be resolved. The third one is network representation, right? So people use just a simple multi-layer perceptron. This is the traditional pin way of doing things. Could use CNNs or GNNs. And within CNNs, there is FNO, right? So FNO is this Fourier neural operator. It's actually a new layer that is used as part of CNN. So it's a different idea, right? But it stays somewhere down in the hierarchy of complexity. Okay, but and last but not least, the loss function itself, right? So there is a data-driven loss function, data-free, within data free, there is pointwise, full-field, and there's a whole hierarchy. Okay. So when somebody is talking about a new method or a new innovation, it's some combination of all these 3 or 4, right? And from an industry perspective, when they see something new, which is like mind-blowing, it's hard for them to pinpoint and say, okay, this is where the innovation has happened. And can I use this? Can I not use this, right? So for them to get clarity on where the field is going, we need some kind of ontology. And even if somebody takes this up and works on the existing literature, that would be huge value. The second piece of ambiguity is benchmarks. That is, what are these new technologies that are coming up? What are they actually solving, right? And there are so many different ways to measure these, right? So if you fix a problem, let's say somebody is saying, have a better Navier-Stokes solver for higher Reynolds number, okay? Then the question becomes, okay, how do you compare that with something else, right? Some benchmark. So for that, we need to have a clear definition of the data sets that we want to use for measuring performance, be it geometries, boundary conditions, initial conditions, forcing functions, etc. And ideally, these have to be very industry specific, right? So let's say in the automotive industry, let's say for cars, there are specific geometries that everybody works with, like Ahmad body and some other geometries that they work with, right? So if the data sets are fixed and the geometries are predefined, then any new innovation in that space will have real value for industry, right? They can quickly go and say, okay, this better than this, let me use it. Same thing with accuracy, right? When you say better, it needs to have specific metrics on how we want to measure better, right? It could be accuracy, training performance, and inference performance. Okay. So with all this, the bottom line I'm kind of trying to get to is there is confusion in terms of where these fields are, and there are opportunities for researchers like yourself to actually pursue, which is both around ontology and also benchmarks. So the link I have here, so the first time I gave this talk was a month back, and at that time, I don't think this benchmark existed. So in the last 1 month, right, this paper got released on October 17th. So now there is actually benchmark for scientific machine learning. This is the first attempt towards that. And if somebody's interested, I can send that link for you to get a feel for it. So definitely people are working on this space, and this is fairly new. So the second challenge is scalability. Okay, so most of the work that you might have seen is probably smaller 2D problems that to demonstrate an idea. But when it comes to real world challenges, you're talking about scale, right? You want to solve it like large scale to resolve a lot of physics that is hard to resolve with smaller resolutions. So within that, let me give you an example. Okay, so let's take a Poisson equation. Okay, so I have this again steady state diffusion elliptic equation, and I have my input diffusivities, that my nu in this case as input to my neural network. So in this case, my neural network is a 3D unit, and my output is the solution of this, right? So that is in this case, I'm computing u for the solution. So when you're actually training these networks, okay, you're going to train this on GPUs, right? So the idea here is you use one or many GPUs, and you want to train this network. And when you look at the GPUs, they have relatively small memory footprint. Okay, so 32 gigs, 40 gigs. I think the latest is 80 gigs. Whatever it is, there is still a ceiling for the amount of memory that you can have on a GPU. Okay. So the plot I have here is peak memory consumption with respect to the volume itself. Okay. So for example, for 32 cube, for a given network, by fixing obviously all the other parameters, I can show that after 128 cube input volume, none of the GPUs can take in even a single data point, right? And when you have that kind of a large memory problem, you need to scale out. Okay, so these are typical HPC clusters where you stitch together a whole bunch of nodes, where each node has a bunch of GPUs. You have a parallel file system, and you have an Ethernet band network that communicates across these. Okay. So training on a multi-node, multi-GPU HPC cluster becomes mandatory. So we did that, right? So we actually said, okay, we can't solve this on a single GPU. Let's throw more GPUs at it, okay? And now the problem basically can be solved. So we actually were able to solve a 256 cube problem, used 8 GPUs in this case, and the batch size was 16, and it took us 34 hours of training time, okay? So the problem here is throwing more GPUs at a problem. Yes, sure, it can solve it, but it is not sustainable, right? Let's say I want to change the network and retrain it. I have to spend 34 more hours, right? This is whenever I spend hours on GPUs, it's actually money out of the pocket. So this goes into the investment side of building a model. And if building a model is a lot more expensive than actually just solving the problem using traditional methods, then there is no clear value from all the scientific machine learning technologies that we are building. Okay. So the opportunity here is, can we actually train these networks without just throwing more GPUs at these problems? Okay. And that's where the opportunity of actually coming up with better algorithms exists, right? So this is an opportunity for HPC algorithmic innovations. So let me walk you through one work that we did, which gives you an idea of what I'm talking about when I say HPC algorithmic innovations. So I don't know if you're familiar with this method called Multigrid for solving PDEs. The way Multigrid works is you basically train your networks, okay, using a hierarchy of meshes. Okay, so in the traditional way of using multigrid, you solve the PDE using a low resolution data, and use that solution to resolve a high resolution, and you use the resolution or the solution at that point to solve a higher resolution problem, right? So you basically go hierarchically to solve problems at different scale. The same idea can be used even for building neural networks, okay? So the way to do that is, instead of training the whole thing at, say, this like 256 cube resolution, we don't have to train the whole thing at 256 cube. We basically do incremental, right? So you start with 256 cube and not go through all the 100, 200, 300, 100 epochs to train it completely. You train it to a little extent, and you use those weights for a lower resolution training. And you can use those weights to train a much lower resolution training, and incrementally update your weights. Okay, so the idea is, don't solve the whole thing at the highest resolution, but use the information from training the same thing at lower resolutions. Okay, so it's basically the strategy of multigrid is what we kind of used here, right? So to be a little more specific, the way it works is, instead of actually saying, okay, I'm going to use the same neural network architecture across all resolutions, I'm going to use, let's say I have two grid sizes, okay, 64 and 128. The first thing I'll do is I'll train my neural network using 64 cube input data with a depth 4 unit. So depth 4 just means I have 4. My depth of this network is four levels, And I'll train this network using my input data to say some 10 or 20 or whatever, like small number of epochs. And because I'm using a lower resolution data, this training should be fairly quick. Okay. So now I'll use this thing as part of my bigger network that I need to use for my higher resolution data. And when I do that, because I'm actually starting not from some random initialization, but something that has already been learned, the hypothesis is the training on this network should be faster because I'm not starting from random, but I'm actually using some information. Okay. So when you start doing this, there are different ways to go in terms of training, right? You can start very fine, go all the way to coarse, and go all the way to fine. You can do a W cycle, you can do a half V cycle, you can do a whole different types of architectures in terms of multigrid itself. Okay. So we've done a lot of experiments around this, and the best speed and accuracy we got was with respect to V cycle. So when you do this kind of algorithmic innovations, the benefit is as follows, right? So we took the same problem and trained it on 8 GPUs on Azure, and instead of taking 2000 minutes, right, which is around 34 hours, we could actually train the same problem to same loss in 150 minutes, right, which is actually a 13 times speed up to build the same exact model. Okay. So in terms of cost, it's pretty significant, right? So basically, using multigrid, we spent $55 on cloud. And using standalone, we had to spend around $750. Okay, so industry cares about this because these numbers would actually go into their own business case that they need to present to their management to say, okay, we have to pursue scientific machine learning because it doesn't cost much. At the same time, we get these many benefits, right? So this idea of algorithmic innovations could mean a lot for industry, but not so much for academia. Okay. So training, so we went even further, right? Training 512, it would have taken us 50 days to converge, but we got the solutions in 500 minutes. So as the resolution goes up, these algorithm innovations will actually have a lot more benefit, right? So in this case, I have 140, we can demonstrate 140 times speed up in training. Challenge 3 is deployability. So fine, we've understood what the networks are, what the complexity is, we've built a model, then what? Okay. So there is an entire existing scientific computing ecosystem built over several decades, right? So we have OpenFOAM, we have MATLAB, ParaView, ANSYS, a lot of internal homegrown software, a whole bunch of open source coming up, including NVIDIA Modulus, and a lot more will happen in the future. So any new system that we're going to build has to work alongside these existing tools, right? So it can't be standalone, and it has to work by itself. So it needs to work along with this. The second piece of this is operations itself. So there is a complexity of scientific computing, but machine learning by nature has so many things that have to happen, right? So you need to come up with a concept, a thesis. You need to come up with the data. You need to analyze the data. There is a data analysis part. There is a training. There is deployment. Way too many pieces that have to go hand in hand. That one needs to iterate several times to reach a system that actually works. Okay, so there is a lot of operational aspects to it. So the opportunity here is come up with the right solvers and a platform that can help either service providers build the solutions or give these things to industry so that they can build it themselves, right? So there's several ways to think about it. So one way to think about it is like give SciML solvers that are easy to consume. Okay, that is give the industry a black box or a gray box where all they're doing is they're passing in their geometry models, whatever is relevant for them. And everything in here is completely abstracted out, like whatever training, whatever inferencing, whether it is forward problems, inverse problems, everything is kind of in this box. And all the user is doing is they have a browser-based UI with some kind of in-situ visualization, along with an ops module, right? So an ML ops module is basically where you're actively looking whether the model that is built is working as expected. Because unlike traditional solvers where they can give you an exact metric of errors and tell you what's happening, deep learning comes with its own inherent uncertainties that somebody needs to keep monitoring, right? And so this is one way to think about it, that is coming up with a black box where it's a kind of a plugin where people can just pass what they want and they get the solution, okay? And easy to use. The other way is, okay, somebody wants to build their own models, right? So it's not a plugin, but there are a group of data scientists trying to build all this. So in that case, they need a platform. Okay. So when I say platform, think of it as a very typical machine learning platform where there is going to be some kind of model discovery. So in this case, they're doing data exploration, data transformations, building a model. So this is where all the things that we talked about in the first two challenges come in, right? So what is the input data? What is the data representation? What is the network architecture? All those things are happening on the left-hand side box here, where these data scientists and researchers who have experience with scientific computing and also experience with machine learning are trying to build these models. And once they build the models, they go into these deployment phases, right? That is, these models have to go either integrate with existing tools or have a standalone tool, whatever that is. But the model built here on the left-hand side will be used here. And this part has its own challenges, like how do you monitor it? How do you create alerts when the model is not behaving as expected? And who gets the alert? And who is responsible for retraining this model, right? And how do you back off the model when it is not performing well, right? So all the operational aspects also become an important challenge that industry has to deal with when they are building their own models. Okay, so all these pieces have to come together. So that's kind of my half-hour quick run through on different challenges and opportunities. So to summarize, there is no doubt scientific machine learning is the future for scientific computing. So it's right now as we speak, it has compelling value proposition, and there is a lot of push from Department of Energy to use this for building energy efficient data centers, to designing new materials. There's a lot of work going on in this space, right? And obviously, there are a lot of opportunities for contributions from academia and researchers. That is, starting with ontology and benchmarks, just clear out everything that is going on in this space and put a structure around all the work that is happening. Nobody is actually taking a good lead on this. The second thing is HPC scalable solutions. That is, different problems require different techniques, and just throwing more compute, more GPUs doesn't cut it for industry, because this is a cost that they need to justify to go after a solution. Okay, and even if somebody is a solution provider building a solution for a certain industry, it's a cost for the solution provider, because they'll pass on the cost to the industry. So one way or the other, throwing more GPUs at a problem is not sustainable. And number three, you need to think about SciML more in terms of operational challenges, in addition to just theoretical demonstration challenges. Okay, so until we solve these operational challenges that are more relevant for industrial integration, we are not there yet. Okay. So we are, there's a lot of progress, there's a lot more to come. And with that, thanks for your attention, and I can take any questions.
Thanks so much, Santi. Great presentation. Any questions, guys? Put them in the chat and we'll take them one by one. Seems there are no questions. Could be a good or a bad sign. Could be both. I also don't have a question, maybe on the physics aspect. I always ask the same question. If you also work with experimentalists, because I feel if you train a machine learning model on that data alone, which comes from a simulation, feels that there is an inherent bias in the data. How do you overcome that?
So there are these GAN-based architectures that a few researchers have been proposing, where they actually, instead of just using the physics, they try to also use data as part of the neural network training, right? So they impose the physics that they know, some kind of constitutive equation. In addition to that, they also say, okay, I have this data, let's make sure my model is not just behaving as per the equations, but also using my data to come up with a model that is a little more realistic, right? So it's a matter of coming up with a different architecture and different problem formulation to enforce what is known from literature and the data.
Right.
Did I answer your question?
Yeah, that makes sense. Joseph asks, do you know any existing scientific machine learning Git repos for learning?
Yeah, absolutely. So there is a lot of work from Brown University. So there is something called DeepXD. So let me, DeepXD is a good one to get started. NVIDIA has NVIDIA Modulus that is going that's very active. So yesterday they had an entire webinar on that. These two might be good starting points, right? And I can also give you a link for this benchmarks paper, and that might have more references for you.
Great. Cool. Thank you so much. Odok, you have a question? Go ahead.
Yeah, I have a question. So you mentioned that some researchers are proposing GAN-based architecture to marry the physics and the experimental data.
Yeah.
So I don't know, can you just give a descriptive run through on how that will work? Because I read a couple of papers using conditional GAN to for inverse problems, and I noticed that you still have the same thing as your data inputs being simulation data of that sort. So I just it's hard for me to imagine where experimental data would fit in that.
I see. Okay. So let me pull a paper and flash that. I think that'll be. I can walk you through a specific thing. Give me 1 second. Huh? So I'm sharing my screen again. So this is a paper from our collaborators from ISU and NYU. So let me go to this. Can you guys see my screen?
Yep, that works, Santi.
Okay. So, so you in GANs you have two networks, right? One is the generative network, and one is the discriminator. So the way the data comes in is, so for the generator, you actually pass in your control parameters, which is, so let's say in this case, within my Poisson problem, I pass in my diffusivity, and out comes my, let's say, my solution to the PDE. Okay. So I can do, the loss I apply there would be my my actual physics equation, right? So the PDE that I'm going to enforce, and my data here would be actually the measurement data, right? So that is whatever the counterpart of this that I'm measuring can go as my input to my discriminator. Okay. So when I pass it to my discriminator, basically what I'm saying is, okay, make sure that I'm learning whatever I'm learning, both from the data as well as my model. Okay, so the generator itself eventually won't be just limited to learning from my PDE, which is an equation. It is also going to learn from my from the data that I pass. Okay, so I'll take a pause there, and is that clear? Or if you want to want me to?
Yeah, it's clear.
Okay.
Okay, yeah, it's clear. Thank you. Can you please put a link to the paper in the chat?
Yes, will do.
Thank you.
And just to add, right, so if, for example, if somebody is solving, say, an inverse problem, that is the input to the network is actually the measurements, right? And the output is a control parameter. You could do the same thing. That is, you can say, okay, this is the control parameter I need to satisfy, and just reverse the whole thing. Okay. And I think these guys also use some of these techniques for topology optimization. So I think the best bet for you is actually go look at some of these authors, right? Like ISU and NYU folks are doing a lot of work in using GANs for a lot of these scientific machine learning problems. Okay. So I'll give you this paper, link to this paper, and the best, one thing you could do is check out respective publications from this group. Okay.
Thanks, Atan.
So I have a small confusion. So when you showed about that multigrid architecture that we use for the neural network, so because I believe that you are solving for the Poisson problem, so was the motivation taken just for the like the damping of error component, or will that architecture also work for the different class of PDEs that you are solving?
Excellent question. Excellent question. Yeah. So let me send the paper for the Poisson problem. Okay, it was actually one of the SE papers that got published last year. Okay, so you have more material on what the technique is. No, so we used Poisson as a demonstration to do it at scale, but the same idea also worked for other equations, right? So we actually use the same idea for solving fluid flow problem. It's Burger's equation, where it is more of a hyperbolic system than an elliptic system. Okay, so the motivation kind of came from Multigrid, because the idea was, okay, can I use learning from a lower resolution to higher resolution has been there for a long time, right? But how does that actually translate into machine learning and deep learning, and how do you formulate the training, inference, the whole, like the mechanics of it, right, is not very well established. Okay, so when you look at Multigrid, there are all these pieces. There is a smoothing component, there is an extrapolation component, there is a interpolation component. So there are a lot of these components in traditional Multigrid from a linear algebra point of view, right? what we were trying to figure out is what are those kind of mappings in the deep learning space. And we've applied that for Poisson and demonstrated that when you do it at scale, you have real benefits. But it works in other equations also, Nishant. We have tried in other places. Obviously, it is not exhaustive, but that is something for one of you to pursue.
Okay, sure. Thanks.
No problem.
All right. Any more questions? Santi, would you be able to share me the link of the presentation? Maybe I can share it with the audience as well.
Yeah, I can just translate that into a PDF, and maybe I'll just email that to you. Will that work?
Yeah, that works. Perfect. Thank you so much. There's another question. How much data is enough data for machine learning if benchmarks are not available? That's a good question.
That's a very good question. I mean, I think I get that question very often. So, I mean, the answer is it depends, right? So the more important to find a metric to say it's enough for your own problems. So let me elaborate on that. Okay. So for some applications, okay, you don't need to go to an accuracy of say 10 power minus 8 or 10 power minus 6. So in a lot of industries, so for example, when I worked at Intel, to design something, coming up with a solver which has an accuracy of 10 power minus 3 is sufficient to make a design decision. Okay. But let's say you're doing something in the field of healthcare where you're designing something that actually goes into a patient's hip or something, right? Then your accuracy thresholds are much lower. Okay, so assuming data directly has an impact on accuracy, okay, how much data is sufficient is completely depends on what is the problem you're solving. Okay, so for that, it's not a machine learning problem, it is actually an application problem. So more you understand about the application that you are trying to address, better you have the understanding of the data, how much you need, and different problems will require different data sets. And again, if benchmarks are not available, it's the current state, but that is changing very quickly, right? Like I pointed out the paper. We were talking about benchmarks 3-4 weeks back in a different context, and 2-3 weeks since then we have benchmarks, and benchmarks are going to grow. But none of these benchmarks are going to help in actually completely solve the problem. It again goes back to understanding the application very well for to determine how much data is needed. Okay. Yeah, hope that helps. There's a lot more intricacies in the data piece, but in this context, accuracy could be is a sufficient metric.
Great. All right. If there are no more questions, Santi, thank you so much for doing this.
Yeah.
You'll also be soon invited to the podcast, so prepare for that. I think people will be very much interested to hear what you have to say. But yeah, thank you so much, and hope to see you in a second part in the future.
Absolutely.
Appreciate it.
Thank you very much. Thanks for inviting me. Thanks, everyone.
Bye-bye.